Hello again, and welcome to this video workshop presented by Macnica Americas. In this presentation, I will walk you through the details of creating a custom FPGA design to enhance the capabilities of the Mpression MAX 10 FPGA and BLE sensor kit. I'm Troy Jones, a member of the technical staff here at Macnica Americas, and I will be once again leading you through this virtual workshop, the fourth in our IoT series. The primary goal of this workshop is to teach you how to create your own MAX 10 FPGA design for the Odyssey kit using the Altera Quartus 2 suite of tools. I'll first go over the details of the Odyssey MAX 10 FPGA and BLE sensor kit. That will include covering the FPGA configuration that is used in this workshop and the data flow from the smartphone down to the FPGA itself. I'll give you a simple checklist you can follow to make the whole process easy. I'll cover what tools are going to be needed and where to access them, including where to get the reference designs. From there, I'll get into the details for modifying one of these reference designs. For this workshop, we will be adding an I2C slave register that controls a series of LEDs attached to GPIO pins of the Odyssey. In order to control this new register, a new smartphone app will be required. I'll show you how to use the cloud-based web utility to do just this. Once the new FPGA design is done and the new smartphone app prepared, I'll show you how to use the embedded console menu system to load the configuration into the Odyssey Flash. Now, this workshop is designed for engineers that are interested in using the highly integrated framework of the Odyssey system but are not familiar with designing an FPGA. I'll give you the fundamental skills necessary to create your own design and program the Odyssey. However, this class is not designed to be an in-depth FPGA instructional course. There are countless resources, tutorials, webinars, live trainings, and additional virtual workshops available from both Altera and Macnica. At the end of the session, I'll give you a few links to access these resources. Let's get started by doing a quick overview of the Odyssey system. The Mpression Odyssey MAX 10 FPGA and BLE sensor kit actually is comprised of three separate boards: the BLE sensor board, the FPGA board, and the battery board. Now, the kit will come shipped in the FPGA configuration. I'll cover that more in just a slide or two. Many details of this kit are available in the user's guide at the link provided here. So, for the three boards that are included, let's look at some of the specific details. The heart and soul of the Odyssey kit is the BLE sensor board. This is where the Broadcom Bluetooth Low Energy device is, the Silicon Labs EFM32 microcontroller, the memory, the power, and then all of the sensors, which include an accelerometer, temperature and humidity sensors, and then proximity, light, and a heart rate and blood oximeter as well. The FPGA board, the one we're primarily concerned with today, is where the MAX 10 FPGA resides. Also on this board are the LEDs, switches, and push buttons. There's also a MEMS-based microphone, as well as additional power regulators. There is also a JTAG interface if you wish to directly program the MAX 10 FPGA. Now, on the bottom of the FPGA board, there are dual inline pins that can be used to expand the capabilities of the FPGA board. The third board included in the kit is the battery board. This board is designed so that you can power the BLE sensor board off of a coin cell battery so that you can run a true wireless system. Also integrated onto this battery board is the microcontroller interface as well as an I2C expansion port. You have heard me mention a couple of times now the FPGA configuration. All this is simply the BLE sensor board attached to the MAX 10 FPGA board. This is the configuration that we will be using throughout this workshop. Let's take a closer look at the block diagram of the FPGA configuration of the Odyssey kit. You can see on the BLE sensor board that all the devices communicate over either an I2C or a SPI bus. It is over the I2C bus that the MAX 10 FPGA communicates to the BLE sensor board. You will also notice that the microcontroller is connected to the FPGA by JTAG signals. This is the primary means by which the FPGA receives its programming data. That covers the basic hardware details of the Odyssey kit that we will be using for this workshop. Now, let's address how you will control the kit. Both the hardware configuration and the smartphone app configuration are defined by a single personality. From the hardware point of view, this is the setup of the sensors and the programming of the FPGA if needed. This portion of the personality is stored in the flash on the BLE sensor board and includes the FPGA programming file that I will be showing you how to create. From the smartphone point of view, this will be the actual user interface on the phone that will be used to control and interact with the Odyssey. This portion of the personality is stored in the cloud and is created by using the web utility that I will demonstrate later. Once a personality has been defined and loaded into both the hardware and the smartphone, you will be able to interact with the Odyssey by using push buttons on your smartphone. Basically, when you push a button on your phone, the Bluetooth device on the Odyssey receives the command and will either process the command or pass it onto the appropriate device for processing. For this workshop, this is the flow we will use to issue an I2C command that controls LEDs. Here is the checklist I recommend you follow to achieve the greatest success in creating your own FPGA design for the Odyssey system. I'll be going through each and every one of these steps now to show you how exactly to do them. I suggest keeping this list handy. Okay, first things first. Let's at least take a look at the personalities that are shipped with the Odyssey kit. So I'll show you how to simply power up the kit, launch the smartphone application, which will require an account on the web utility. Then we'll connect to the device, select a personality, and interact with that personality. So here we go. The first thing you'll need to do is download the Mpression Odyssey smartphone app from either the Play Store or the Apple Store, depending on which flavor of smartphone you're using. The easiest way to find the app is to search for Mpression Odyssey. Install the app and allow it access to your Bluetooth radio. Now launch the app. Before connecting to your Odyssey kit, register so that the application can access the default personalities in the cloud and, in the future, your custom personalities. Once the registration has been submitted, a verification email will be sent to the address supplied. Simply click the link in the email to activate your Mpression account. Return to the smartphone and log in with your new credentials. You can see here the app automatically starts scanning, looking for the Odyssey device. Now power up the Odyssey hardware by simply plugging it into a USB cable. Remember, it's not necessary to have the device plugged into a PC power supply. Any 5-volt USB supply will work. And remember, there are no indications on the device letting you know if the power is on or not. By now, the app most likely stopped scanning, so touch the scan button to start it again. You will see the Macnica_Mpression device with its Bluetooth MAC address. Touch on the device name to connect and open the personality list. You can now see all the pre-installed personalities. Go ahead and choose one to play with it. I'm going to pick the PWM LEDs since it has visual feedback. The phone app reports that the personality is loaded successfully. An important thing to know here is that this message only applies to the smartphone app. For any of the personalities that require the FPGA to be programmed, there will be a 3-second delay, and then the device busy LED right here will illuminate while the FPGA is being programmed. Don't try to use the personality controls until the FPGA has fully programmed. It takes only a few seconds. You will know when the FPGA is done when the device busy LED turns off. In a future release of the phone app, the app won't be activated until the FPGA is ready. Go ahead and play with the personality controls. Recall from earlier, what is happening is that as soon as a button is pressed on the smartphone app, a Bluetooth message is sent to the Odyssey that contains a command for the device to execute. In this example, an I2C command is being sent to the FPGA to control the LEDs. To change the personality of the Odyssey device, simply return back one screen and select another personality. Depending on the one you choose, the FPGA may or may not need to be reprogrammed. In this case, for the temperature and humidity personality, the FPGA is not required, as the BLE device has direct access to that sensor and can issue commands and retrieve the data directly. Please pause the video and play with the other personalities that are available. If you want details about what each of them do, just touch on the description button to open a web browser to a page that contains all the details for each. Now those personalities are great and all, but what about creating your own? And more importantly, what about creating a personality that has an FPGA design that you create? You'll need two things in order to create your own FPGA design: the FPGA design tools and a reference design. The MAX 10 FPGA toolchain is called Quartus 2 and is available from the Altera website via the download links at the top of the page. Scroll to the bottom and click on the Select by Software tab to display the list of all Altera software packages. For the MAX 10 FPGA, the free web edition version 14.1 includes everything you'll need. As you can see here, I'm going to minimize my download by choosing only the features of Quartus that I really care about right now: the main Quartus 2 software, and only the MAX 10 FPGA device files. Once downloaded, launch the installer and follow the prompts. As part of the installation process, drivers for the USB JTAG programming cable will be installed too. All said and done, my download and install took about 20 minutes. Next, let's get a reference design so that you can start from a known good working set of files. All of the pre-installed personalities are freely available on the Mpression website as well as the Altera store. I'll show you how to get them from the Mpression site here. Just go to the Odyssey MAX 10 FPGA and BLE sensor kit main page and select Software Downloads. This will take you to the page where all the factory installed personalities reside, as well as the Quartus projects and full source. There are a few other utilities and manufacturing details here as well. Find the link for the Quartus 2 project files for the MAX 10 remote personality. That's the I2C template.zip file. This zip contains all the RTL source code as well as a complete Quartus 2 environment. Download and extract the zip file to a location of your choice. You can see here I placed the project on my C drive under my projects folder. Included in the project zip are folders that contain some IP blocks. Factory generated FPGA programming files are in the master image folder, and the output files folder contains reports and other intermediate outputs for the Quartus tool run. The RTL folder has all the clear text Verilog source for the design, and the scripts folder contains timing information. The remaining files are project archive and other necessary project settings files. Here is a link you can use to access Quartus 2 tool suite, and two links to access the reference designs. The first one is hosted by Mpression, and the second is the Altera store. Before digging into the design files and changing them, let's take a look at what the I2C template design gives you. Basically, this design creates the I2C slave interface with a few registers defined inside the FPGA. Now, it's highly recommended that you start with this design and expand it to meet your own needs. The Mpression team has taken time to test and verify the functionality of the design, and the I2C slave and register blocks are designed using the OpenCore's widely accepted open source IP. As you see in the block diagram, at the top level we have a PLL receiving a 50 MHz clock, a couple of static registers, and the I2C slave. Inside the I2C slave, we see the serial interface and the register interface, which has 4 registers. 3 of them are tied to inputs, and one of them is tied to the LED's output. Recall that the I2C bus is the communications link between the FPGA and the Bluetooth device on the BLE sensor board, and the switches, buttons, the oscillator, and LEDs are all on the FPGA board. The I2C slave address has been defined to be 30 hex in the reference designs, but you can easily change this by modifying the value in the I2C slave _define.v Verilog source file. The registers are simply an offset from the base address, and we'll see this more clearly coming up when we modify the code. Alright, let's get down and dirty. Time to change the source code to include some customizations. What we're going to do is add in a 5th register that, on command, captures the position of the dip switches of the FPGA board and then displays the pattern on LEDs that are connected to pins of the dip interface. Here's what it looks like in terms of the block diagram we just went over. Here's the new register and the connection to the dip interface of the outside world. Basically what we're going to do is create a new register that when its address is accessed, it takes a snapshot of the switches and stores it. Now, in order to get this information out to the pins of the dip, we must punch through the upper layers to get the signals out. This is called port mapping. Let's start by launching the Quartus 2 tool and opening the I2C template project. The Quartus project has a QPF file extension. Take a minute to look at the user interface, and you can see things like the MAX10 FPGA device part number, the individual subprocesses of the tool flow, the IP catalog, and the messaging interface. The RTL source can be seen on the Files tab here. Now, the first Verilog file we're going to change is the top level, top.v. We are going to add in the top level port to the dip pins. We'll call it My LEDs Out. Referring to the new block diagram, we can see this output port is going to be driven by the I2C slave block, so we need to add a port to this entity here. You will see why I use the reg4_ nomenclature once we make our next modification. Save this guy and let's move on to the next one. Open the I2C slave.v source file. Again, looking at the block diagram, you can see we need to punch through this block to get down to the registers. We are not adding any logic here, simply port mapping. We will call the I2C slave port reg4 my LEDs out to match what we did in the top level a second ago. This will be declared as an output of this block. Next, scroll down to find the register interface instantiation and punch through this layer with our reg4 my LEDs out signal, like this. We're done here. Save and open the lowest level register interface.v source file. Similar to the other two files, we need to create a port at this level, the reg4 my LEDs out, and declare them as outputs. Next is where we create the actual storage register that will capture the switch settings as discussed. We'll call the register reg my LEDs. Now scroll down to find the process that actually monitors the right enable line and decodes the address as provided by the serial interface. We see here that the original source code only decodes one address when the I2C slave is written to. Now referring back to the original block diagram, we can see that this is the LED register that drives the LEDs of the FPGA board. Now, since we're wanting our register to drive the LEDs connected to the DIP interface, this would be a good place to add in our register. We will define this register to be at offset 04 hex, and when it is accessed, we will capture the switch settings. Finally, we need to drive the top level ports of this newly created register here. I'll invert the values driven out since the LEDs connected to the pins are active low. That's it. Those are all the source code mods we need to make. But you may be asking, how do we tell the FPGA what pins to drive this new register out on? Well, that's a good question. To do this, we need to let the tool chew on the modifications we just made and then tell the pin planner which pins to use. To get to this stage, we only need to run the analysis and synthesis process and then start the pin planner utility. We can see here that the process picked up our 3 new LED outputs, but has yet to assign them to pins. Simply click in the cell and enter the pin locations. You can find the pinout for the DIP on the schematic, available under the Documents link of the Mpression Odyssey Kit main page. Close the pin planner to save the changes. We're done. Well, with the design entry at least. The final 2 stages to get our custom FPGA design ready for the Odyssey kit is to let the Quartus tool run a complete compile and then generate the correct FPGA programming file. Simply double-click on the compile design process and everything needed to complete the flow happens automatically. It takes only a few minutes to complete. You can safely ignore the red time quest notification, as it is simply telling us that there are no timing constraints applied to our new LED output signals. With the compilation complete now, we need to create a jam staple bytecode formatted FPGA programming file. Well, that's just a JBC file. To create the file, we use the programmer. Double-click here to open the interface and then add in the default Max 10 device programming file, the SOF. It's located in the output files directory. With this file added, we can create the required JBC file like this. Be sure to select the Jam Staple Bytecode 2.0 JBC option from the drop-down menu. Name the file whatever you like. By default, the file ends up in the output files directory. That's it. You just created a new custom FPGA design that can be used in the Mpression Odyssey MAX 10 FPGA and BLE sensor kit. Now recall from the beginning of this workshop that a personality is comprised of 2 parts: the hardware, which we just completed, and then there's the personality control via the smartphone app. To create a new personality to control your new hardware, we will use a cloud-based configurator. This web utility is accessible via the link here. Once logged into the web utility, you will once again start from a known good personality and modify it to fit your needs. So, without delay, let's get going. You first log into the web utility using the same credentials you created via the smartphone registration to initially play with the pre-installed personalities. The page you are presented with at first is the list of personalities. Notice that these are all the personalities you can see on the smartphone app when you connect to the Odyssey device initially. These are what are defined as public. Anybody can see these. Since our FPGA most closely matches the Max 10 remote control functionality, we will use this personality as a starting point for our custom one. Just click on the Copy and Edit link to create a copy in the My Personality list and open the editor. Go ahead and change the name to something unique to your liking. The URL here links to the Mpression description of the default personality. I'm going to remove it just as a demonstration that it's not required. I'm also going to create a custom teaser field. power of the smartphone app is defined here under the personality controls. You can see the existing commands that are populated as a result of a copy a second ago. We're going to add in a new button to issue the I2C command to capture the switch and display the value on the dip LEDs. So give the button a name. Here I'll use my LEDs. Click the plus icon to add in a new command. In our case, we're going to create an I2C write command to address 30, the FPGA. Now, I didn't talk about it when I modified the Verilog code, but our register is only 1 byte in size. Here is where we enter the offset of our register, 04 hex. It is required by the editor to enter the number of bytes that are going to be sent and the source of that data. We did not write our new register interface such that it captures any command data, so we're simply going to enter a single fixed data value of 1 here. It'll just be ignored in our design. Save and update the control to see the completed control button. Now, we didn't spend all that time creating a new FPGA design just to have it ignored. Here is how we associate that design with this new personality. Select the option stating that the FPGA is required and that the jam player will be run to program a JBC file into the FPGA when this personality is selected. Click the Choose File button and locate the JBC file we created a few minutes ago. Remember, it was in the Output Files directory. Then upload it to the web utility. Congratulations! You have just now created a new personality with a new control button and associated a new FPGA design with it. Now, the last step in accessing the new personality is to save it and download it. When you save, a couple of things happen. You're creating a cloud-based GUI configuration of your smartphone app that'll be downloaded to your phone when the personality is selected. And you're creating a flash file that contains the FPGA image that will be programmed into the FPGA at the same time. Click on the Save button at the very bottom of the editor to generate the smartphone app configuration and the flash file. Your new personality is now listed and available for download. Click the download link to download the gat.bin file to your PC. Feel free to rename it and place this file anywhere you want. Now that you have the personality defined and the flash file accessible, we need to load it into the flash that is on the BLE sensor board. This is accomplished by means of a serial transfer from your PC to the microcontroller and then into the flash. You will need a serial terminal emulator installed on your PC to make the flash file transfer. The Mpression development team uses and recommends the open source TerraTerm emulator, available via the link here. Now, the microcontroller on the BLE sensor board is set up to communicate at a baud rate of 115,200, 8 data bits, no parity, 1 stop bit, and no flow control with the PC that contains the flash file. When you first plug in your kit to a USB port on your PC, it'll automatically enumerate a virtual COM port that you must use with the terminal emulator. On my PC, you can see here via my device manager, the Odyssey is assigned COM27, and here you can see my settings of my TerraTerm session. The Odyssey must be placed into console menu mode in order to modify the flash on the BLE sensor board. To put the system into maintenance mode, press the S3 button on the FPGA board once. The green Device Busy LED on the BLE sensor board will illuminate as shown here. With the terminal window open, when I press the S3 button on the FPGA board, I can see that I have successfully established a communications link. Press Enter to see the full list of available options. First, enter a 0 to see the list of currently installed personalities. These are the default personalities installed at the factory. Take note of an empty slot. This is where we will load in our custom personality we just created. Press Enter again to return to the main menu. Now select option 1 to load our personality file and select the slot number for our custom personality. We will choose slot 8 for this workshop. Now, one thing to note is that slots 11 through 15 are allocated less flash space and cannot contain a personality that require an FPGA configuration file. Use the Terraterm File pull-down menu to send the gat.then file. And be sure that the binary option box is selected, otherwise the transfer will fail. Press the Enter key once the transfer is finished, and then select option 0 once again to see that our personality has in fact been loaded into slot 8. Your new personality, inclusive of a new FPGA programming file, is loaded into the BLE sensor board and is waiting to be used. To access your personality, simply power cycle the system and reconnect to the device just like you did at the very beginning of this workshop. After power cycling the board, press the Discover Devices button on the lower left portion of the smartphone app to scan for the device and select it just as before. Your custom personality is now amongst the available ones to choose from. Go ahead, select it. Like magic, there is your new button. I dare ya. Recall that you must wait a few seconds for the personality to program the FPGA using the JBC file stored in Flash. After the busy LED turns off, play with your new control. Move the switches to different positions and press the button on the smartphone app to see that in fact your hard work has paid off. Good job. Now, the next question you might have bouncing around in your head is, can I change just the FPGA design, well, because I never make any mistakes, and reprogram just the FPGA JBC file into the Flash without going through all those steps? Well, yes, as a matter of fact, you can. The basic flow is to recompile the design and generate a new JBC file, and then program just that JBC to an existing personality. So let's do that real quick. Alright, let's go back to the register interface.v Verilog file. Remember I inverted the output of the LED's register because I said they are active low? Well, let's switch that around just for kicks. I'm going to simply delete the inverter, save, and recompile. Since we're not changing anything else, just the logic, no pinouts, etc., we can just recompile to generate a new programming file. We need to create a new JBC file, and we will use the same flow as before. Start the programmer, add the new SOF file, then create a new JBC. I'll call this one My LEDs 2. Now return to the Odyssey device and place it into Console menu again. But this time, select option 5 to download just a JBC. You will be instructed to send the JBC file. Again, be sure the binary option is selected, and then enter the number of the existing personality that you want the new JBC file to be associated with. In this case, our personality is in slot 08. Cycle the power on the board once again, and re-establish the Bluetooth connection. This time, when you select your custom personality, the new FPGA programming file will be used and the LEDs will start in the opposite state once the FPGA is programmed completely. Again, play with the switches and your control button to convince yourself that the new FPGA design is in place. Now open your mind and come up with something amazing and go for it. You now know what it takes to create a custom FPGA design for the Mpression Odyssey MAX 10 FPGA and BLE sensor kit. Okay, so maybe I overstated the simplicity of the FPGA a bit. This is a very complex and feature-rich device that can enable that wild dream of yours. If you need additional in-depth training on how to use the FPGA, there are countless resources at your disposal, both from Altera and Macnica. Macnica and Broadcom also provide additional details and trainings for those of you that want to customize the Bluetooth capabilities of the Odyssey system. Thank you for watching this video workshop, and if you have any questions regarding any of the content you've seen today, feel free to send an email to workshophelp@macnica.com, and please include IoT4 Max 10 V Workshop in the subject line, and one of our technical experts promptly reply to your inquiry. I'm Troy Jones, and thank you again for watching, and look for our other IoT and Altera SoC on-demand workshops on the Macnica Americas website.